Discord we have to get?
No, not today. Today we're just gonna do stuff. I think people are still rolling in. I'm gonna just wait a few more minutes before starting here. I want to make sure that the stream's up. This is a time lapse of me doing a circuit board.
You doing it right now. I'm like,
No, I'm not that fast. I think this is like 30 times speed going through this design.
Is that your Squid Game stop go design?
Yeah, that's the Squid Game thing. I went and like recorded it and did a time lapse edit. So, where's Nat? Michael, would you look in the Discord and make sure that this link for the stream is working for me?
Yeah, sure thing.
All right, everybody keep up. All right, if everybody wants to get KiCad open in front of them, I think I'm actually going to restart because I started to want to be Arduino because I knew that off the top of my head, but I think we're going to restart that with the Pico. And we're just going to plop it down and then start going through some circuits you might include with your design, or that you'll need to include with your design to actually make that work. As soon as I know the stream's working, then I'll get started here. It's working? Okay, good. Undo my changes here. They changed the way hierarchical sheets work from last time I used them. I wanted to go over it, but I don't think I'll be able to do it well live. This is not the video I was trying to show. Okay. Oh no, we're not starting with any file, so we're just going to start the file from scratch. We didn't really, we popped down an Arduino and a couple capacitors was all we really did last time, so. So if everyone just wants to get a fresh KiCad project open and call it whatever you want, and then we'll get started with this. And I'm going to go back and forth between KiCad and this software here, which is just really nice for showing simulations. You guys don't need to go and draw on this. I'm just going to use it to tell you how a circuit works. Oh, Michael, did you check to make sure the sound is working when you check that stream?
I did not, but
I just realized, because it's pretty darn worthless without the sound. Sound check. Sound check.
it's working, there's just some lady. Yeah.
Okay, good.
Yeah, it's definitely.
All right, thank you everybody for coming back to listen to me talk for 2 hours a second time. I'm shocked. So I said a few times what I was planning to do. I want to go through a few circuits that you're going to want to use possibly in a design that you want to make. Just some simple circuits to use like as building blocks and Legos, and go over, well, I'll go very briefly how they work. You don't need to understand everything about they work if you're not EE. You just understand how you can use it. And then we'll go through what you need to do to route them out and why you might need to do certain things. So to start off here, we're going to use the RP2040 just because that's the microcontroller I'm trying to get everybody to use, so we can order a bunch of them for cheap and put all the boards together, and they're easy to get using. And the KiCad software already has a symbol for them, so we don't need to worry about making it. So if you want to just go to add symbol, I'm sorry my mouse isn't visible. So add symbol in the top right if you guys don't remember, and it should open this dialog up, and just look up 2040. And we're looking for the RP2040, and that's the microcontroller.
That's the Pico.
Yeah, that's the one. So it's the microcontroller that's on the Pico, but let's do it ourselves. We make our own board, and we just plop that down on the schematic here. And if anybody has a good suggestion for like keeping track of when everybody's ready to move on, like I don't know if, because I don't want to like leave people way behind, but I also don't want to go slow so everybody's bored. Does that make sense? So like, if I say let's move on and you need help, completely feel free to go and be like, wait, I didn't quite get this yet. I don't mind at all, or an officer can help you, or whatever else. Okay. So I talked about on the Arduino, we need to get power to the chip is the first thing. So when you're going and drawing a schematic, you don't have to go and have everything figured out right from the beginning. You can just start to try and build how you're going to do things and fill in sort of build the framework of what you're going to do and fill in the pieces later. So I usually end up doing that with global flags or global labels. And that is the button that you can see right here. And I'm going to make one that's V3V3, and that's for 3.3 volts because this microcontroller needs a 3.3 volt power supply. So we know we need 3.3 volts somehow to power the microcontroller. We're not worried about where it comes from this very second. And the only reason I'm putting V in front is because you can't start it with a letter, or I mean with a number, or at least you didn't used to be able to. So when we want to go and make our circuit that's going to provide that 3.3 volts later, we'll just attach that as the output to it. And with what I was saying last time, we go and put positive voltages up, negative voltages and grounds down, inputs on the left, outputs on the right. Generally, you go and look, and that's been followed here, and all of the voltages that we need to supply are up here at the top. So, let's see. I'm going to double check, because the RP2040 is a little bit more complicated than the Arduino, so I might have to check back and forth to make sure I'm telling you guys the right thing a few times. That's what I'm doing right now to make sure I tell you the right things to connect to. RP2040. I'm going to actually look at this footprint because there was something I was expecting to see on it that's not here. So there are multiple I/O VDD pins on the actual chip, and I don't see them here. They might be combined in the footprint. So I'm just going to edit the symbol editor and see if I can see that. Yeah, there we go. So they did this. This was the decision of whoever made this symbol. So there are multiple pins that connect to this IO VDD because it needs power input in the chip more than one place to get the right amount of power. And they're sort of stacked in here in the design. So I'm just showing you guys, you don't need to change anything, but I'm just showing you there are many pins here that are going to be connected. And they're all set to, if we open them up, somewhere in here, they're all set to be invisible and then stacked on top of this IO VDD right here.
If we were to connect the pins to that, they would all go to all of this.
Yeah, because they were all like stacked on top. So like the pin exists, it's right here, and they're all, the little circle around it shows where it's going to connect when you're in this. I'll get into the symbol editor in a bit because this was just a diversion right in a second because I was like, wait, where are all the other pins? I thought we were going to have to connect them all. Actually, I'm going to look because we have to, generally, they want you to add one capacitor per pin. So I'm actually going to look at how many pins are actually here that need connected so we know how many capacitors to add. All right, if I can count, that is 7 pins that are sitting there. I'm just going to go and exit out of this and not save that. What's that? What? Well, that's very unusual.
So
is anybody else having that problem?
If you have versions, and he's using the same installer. If you have version 6.0.5, you don't have the RP2040, but if you have version 6.0.7,
Oh, so they just added. I'm going to go and export that symbol and put it up on Discord for anybody who needs that symbol. We can do that and share it. So you just get the one particular symbol. I didn't know it was just added.
And so you download the file and then just copy and paste it to.
Yeah, so I'm going to go to this just to show you guys how to do that. Also, if you have to do it, I'm going to right click on this and say Edit with Symbol Editor, and this will be where we make all of our changes to it. But I can just go File, Export, Symbol, and it's going to give me the KiCad symbol. So I'm just going to go save that, and then I'm going to go. I'm not going to add it to my library table because I don't need it. And then I'll upload it to Discord for everyone. By show of hands, is there anybody else that didn't get the symbol?
if they downloaded KiCad
Or the
at the last one, they should.
Okay, so it was just, so you're good, you got it?
Yeah.
Okay,
Very well.
so I'll get it uploaded for you, and then you're not.
Or I'll pull it off the Discord because I gave him my install.
Yeah,
That's why
okay.
we both have a problem.
Sounds good.
You have to download.
Who goes there? Come in, don't be shy.
No, we got
Pizza.
Oh, okay. Did I hear somebody say, hey, Jeremy?
Oh, yeah, Jen.
Oh. Okay, that symbol's up. So, just so you guys know, when you need to add a symbol in the future, I'll show how to import that. So, you can do, at the very top here, when you're in the schematic editor under Preferences, there is Manage Symbol Libraries. And in here, you can add a library, and I believe you can also add individual components. So I'm just going to click the little plus down here, and then I can nickname it RP2040, and click the little folder, and then find wherever it is, and add that in there. And then it should add that symbol under RP2040 to it. And when I click OK, it's added to it. I went kind of quick on that, but it's just Preferences, Manage Symbol Libraries, and then you can go and add it in here. And these libraries are like all of the symbols that you have access to. If you were, say, working at an employer that maintains their own symbol library that like matches all the parts you have available in-house and like deals with suppliers, which is actually very common, then you might turn all these off and then only import symbol libraries that your employer was using. I was
nice.
talking to, Suddenly I forget other Justin who went and worked at SpaceX, and he actually, his job there for a while was writing JavaScript to manage their symbol libraries for them over there to do that. Or Jaden, sorry, I don't know why.
Oh,
It was
did you
Jaden.
talk-
Yeah, I talked to him for a while about the PCB thing.
So if you have like octo parts, that's where you took it.
So like, I haven't worked with Octopart a lot actually,
Okay,
but
it's an online library.
so yeah, if you had an online library and you could download it, and they have KiCad format, which Mauser and DigiKey both give you KiCad libraries that you can use with their components. And I don't know about Octopart because I haven't used it. But this is where you would add them in here. So you can also go and add the individual symbol, which is what I did here. And then you'll see when I go to add RP2040, I'll have 2 copies of it. So there's the MCU Raspberry Pi library that has it, and then there's my new RP2040 library that has it. All right, so what I had been saying on the Arduino, so we know we need 7 decoupling capacitors. I'm going to move this down to give myself a little breathing room. And attach this 3 volts to the IO VDD. So IO VDD is just the power supply for the whole board. A lot of times you'll see VCC or something else on there. You just have to kind of look at the documentation of what the power pin is. And then we're also going to attach that to the DVDD pin. That's like a separate voltage for digital signals, but we're not going to worry about separating them. And we need to add the capacitors. So I'm going to go to add symbol, do C__ small, and place these in here. Now, because I know I'm going to need to place a bunch of capacitors and I don't want to edit them a bunch of times, I'm going to make sure that the settings are right before I go and duplicate it. So I just selected it, pressed E to open up this. And typically this is 100 nanofarad, and it looks like that is what they recommend, is to do 100 nanofarad capacitors. Is there anyone who really, really wants to know why you need the capacitor on the power pins?
This is a capacitor.
The-
The C small.
C small, that is the symbol for a capacitor there.
Just to smooth the signal.
It is sort of to smooth the signal. So the deal is with capacitors, and actually I could show this in Falstad real quick.
I'm gonna do an example of capacitors.
You do? Or
401.
yeah, 401 is electromagnetism. And when I was talking to Dr. Rogers, that's where he talks about why we need capacitors for these chips. You don't have to have like the crazy intense class to get the basic gist of it.
I think he makes it harder than you.
And how you would pick a capacitor to.
So let's see here. Really quickly, I'm just going to go and put a voltage source here. So the reality is that connections aren't perfect. They have some inductance to them. And if we have, I'm going to put this resistor right here as the load for our microcontroller. If we look at the voltage that we get across this as we connect, and so every time there's a clock on the microcontroller, it's sort of doing the equivalent of open and closing a switch. There's a little gulp of power it needs every time. So if you have an inductor there, and if we go and look at this, I don't know if these values are going to be good to look at. Why is this not? Oh, there's nothing to look at. Roof scope. It should be showing the. Well, my Falstad has worked. Show voltage. There we go. Okay, so right now it's showing the voltage across this across this resistor over time. We have a fairly significant amount of inductance in the line here. So we have our 5-volt supply, but it's some ways away by a PCB trace or a wire or a cable. And the microcontroller is switching so fast that that matters, and it takes time actually for the current to change because there's inductance in the line. So you'll see the voltage that's here isn't able to change instantly when it needs to.
Like start
Yeah, sort of. Or like spinning up a flywheel or something else, and then also, like, it doesn't change down to, well, in this case it's going to change nothing, but actually there's other inductive effects. So the way we would fix that is by choosing to put a capacitor in, and the capacitor will be, so this is going to oscillate for just a second in here, but this is actually a really large inductor value. So when you go to charge it, it will actually much more quickly, it's not nearly this much inductance. So it will be able to take the current from the capacitor while the inductor spins up, if you will. So if I reset this and, oh, so this is going to, I'm going to charge my capacitor manually here in this simulation. So the capacitor charges up, right? And I need a resistor in here so this actually stops oscillating in this simulation. There's also resistance to it. So ignoring this current for the moment, the capacitor's charged up, so when you flick the switch, it actually draws current from the capacitor right away until the inductor is able to provide, or it's able to provide the current through the inductance. So that's why you have to have one there. I don't know if that was super clear or not, but it's important, and it helps reduce this sort of dip that you get right here in this, if you can see. Right at the time of switching, you get this little dip, and if that goes too low, it could cause problems in your chip. So just provide clean power, and it boils down to follow what it says to do on the data sheet, and it almost always is just a 100 nanofarad capacitor at every pin. Unless it's like a power device, in which case it's more. So, anyways, we're just going to do 100N. And so I set the value to 100N, and I'm going to go to capacitor SMD for the footprint. And I have a whole bunch of 0805 capacitors that we can use when we actually make these. So let's go with the C_0805, and you can type in here to search if you don't want to scroll through.
Are you adding a new symbol?
No, setting the footprint.
Oh, setting.
So here, I'll back up for a moment. So we already have the symbol in here.
Okay.
I'm going to click on the symbol, press E to edit. I'm going to change the value to 100 nanofarads. And then I'm going to click this footprint field here, and the little book shows up to get to the footprint library.
Oh, click the book.
So there's like the little books that show up when you click the footprint line. I'm very sad that my mouse isn't showing because it makes it really hard to show where that is.
Yeah.
Is there anybody who can't get to the footprint library yet because that button's hard to see? All right, it looks like we're all good.
Yep.
So capacitor SMD 0805, and actually I'm going to do the 0805 hand soldering because it makes it easier on us to actually make these. And a lot of times when you're doing an actual design, you want to add in more information. I don't know what capacitor I have off the top of my head other than it's 100 nanofarads and it's 0805. But very often you'll put the data link to the data sheet for whatever device and any other information that you might have that pertains to it here. So when somebody looks it up, they know, oh, they're talking about this very specific capacitor from this manufacturer. And honestly, picking components and putting those in there probably consumes most of the time on doing these type of designs, not the actual using of the CAD software. So I'm going to go ahead and save that, and then that was, trying to remember what the new duplicate button is. Control D.
So your 100N is not showing up, and you have a 100N in the value.
It's not showing up for you. So look it up again. You can hide them if you don't have it hidden. weird. I think possibly you might have accidentally moved your 100 head elsewhere. So maybe just delete the symbol and replace it real quick. And it should be back. It's probably like over here somewhere. But it supposedly.
That's fine. I was just curious. We'll go from there.
So I see the things that I want to make sure it doesn't just happen to you right away. And then you hit OK, it should change it. Oh, there it is. Okay, cool.
So just copy.
So we needed 7 of these from before, and we also have the VDD or DVDD pin. So we need 8.
Oh, wait.
I don't know what the duplicate button is, but you can still just use Control-C, Control-V to copy paste.
Okay. Control D is the shortcut, and then like somewhere near the bottom in here, which is highlighted, there's the duplicate, and it shows you what the hotkey is. And you know what, actually I'm gonna change the way that these are shown so that I can make it a little more compact, because that was gonna take up way too much space. There we go, I think that's clear enough.
Numbers are.
And then I'm going to connect the tops of all these capacitors to V3, V3. And that was with the, what was that?
How many capacitors?
8.
8.
And then I'm going to add in a ground symbol. And I'll stop and make sure, or stop until I hear everybody stop clicking in a moment here. But I'm just putting this in so it's visible what needs to be made.
How did you connect the first capacitor to the V3, V3?
What was that?
How did you connect the first capacitor to
Uh,
the V3, V3 line? I can't put
So I'm not sure. Let me see what you got going on.
How much? Yeah, I was asking like, how did you connect the
Oh, it looks like you did it.
Yeah,
You're good.
thank you.
Mike, I always get micro and mini or micro versus mini USB backwards.
Yeah.
Which one's the one we're usually using on all of our boards?
Yeah, for the
Because
that's
use
micro. and
It's
then-
micro.
Yeah,
Okay.
mini is the older one that you would have on their USB 2.0 mics. You know,
Okay.
that one.
It's just one of those things that's
Actually,
And then USB A, USB C, USB C.
although I think I have a mini in my backpack right now for just my back.
yes, that's what mine uses also.
Okay, I think like USB.
So once you guys have the capacitors all connected up, I want to go and put flags around some of these pins that I know are going to be circuits we're going to connect elsewhere that aren't going to be convenient to show right next to the device.
Micro.
Okay.
Mobile phones or headphones?
Thank you. So particularly the USB VDD and ADC, or not, so not that, sorry, the USB VDD, we're going to need one for that. And this is USB data plus and data minus over here. We're going to need connections for that also. And just name them the same thing as the pin so we're not losing track of what we named them.
Oh, is that DM or?
Thank you. I think I'm actually going to reduce the font size of these just a little bit so that it doesn't overlap like that. So I just double clicked on it to bring up the properties, and I'm just changing it to 1.1 millimeters so that it's actually defined instead of them overlapping each other. And
Just use a label for the 3 volt.
yes, a global label specifically. So the global label on the very right, I'm trying to make it flash right now.
Oh, yeah.
That's the global label button.
That's the one I've been using just for all labels, so it's good to know there's a difference.
Yeah, so this is the global label that's going to go across all sheets that are part of your drawing, as opposed to a net label that's going to be individual. For the most part, I use global labels anyways.
Okay.
The net labels, part of the reason I don't use them is they don't have like a flag around them. I will use them, but I'm not going to use them for the sort of air wires because they're not very visible, and it's just that's more of a stylistic thing. So, and also when you go to route the circuit board, if you use all global labels, then you don't have any nets that have the same name accidentally, and you have to try and understand which is which later.
Right.
So,
Yeah.
It's on the side.
here, I'll leave this up so everybody can see it instead of shaking it around while I'm thinking.
Oh, so we're just adding a link.
So basically labels are the things that will be physically
Oh. Yeah, a label. So if you have two things and you have the same label attached to them, they'll be connected in the circuit board.
So they'll be connected outside this particular PCB. Like they'll be connected physically.
Yes, they will be connected physically. So the idea is like I did this V3 label here,
Yeah. So it
and we're the very next thing we're doing, we're gonna make a circuit that provides that V3, and it's gonna have it like as the output.
That's the input basically, and these USB are the USB ports.
Yeah. Have you ever
Yeah.
used LT Spice? Oh, okay.
What? Yeah.
Yeah, there's a lot of schematic designers, and basically what you do is you have circuits labeled with certain points so that you can kind of clean up the design. Otherwise, you have to have all these wires crisscrossing everywhere.
Okay.
If anybody wants to get up and get pizza, I'll wait a moment
Yeah, I think it's
since I got here. I'm gonna get a slice myself.
Yep. Just do on. Do capacitors or see clean signal.
Let's go. Yeah, you just select it.
Place that.
acid? Is it?
Oh, so it's SMD, it's
SMD.
805.
Let's do SMD.
Yeah. So you do, yeah, you do SMD in the first filter, and then in the second filter you can do 805, and then here you want to scan.
We were doing
Copy and
ones,
paste that.
we were doing ones
You can
about
eat.
that big with Josh and stuff.
Makes sense.
Is that, you guys, I'm pretty sure.
Yeah.
One
So
of
far.
them were-
And then just add, so you just need like what's that?
Oh,
Yeah, I forgot the plates. Did everyone?
we were for sure had a couple of them.
Sorry about that.
We're playing.
We have cups too.
I just screw it up.
Yeah, but,
Yeah.
yeah, there were super big stuff.
I might have it. I don't use it.
I've even tried this out, something that's small. You just have like really fine needle points
Yeah.
on our tip, or?
I expect less people to, but let's use the pizza this.
They might try it. These size ones don't look too bad.
They might not, they might not. They will.
That's still pretty small. Wow. Man, I can smell that. Sorry.
Because it really wasn't that. That's all the stuff.
That would be an amazing PCB to get. You're just like, I can't do anything with it, but look, I powered this microcontroller. It's got 8 capacitors.
Is that basic? Ever since I love me, you always had a cup.
Oh, you're ray tracing.
Ever since I love me, you always had a cup of coffee. All the time. It's people putting it right here. You love coffee. You need to add some sugar in there, because if it's not sweet.
Supreme Court, I didn't know there was a conflict.
Yeah.
So I was at the break. And I didn't go in this room for the first time until like 3 months ago, 4 months ago. Like, I thought,
Wait, is this the coffee place?
actually, no, I was here in like September. But I didn't do, yeah.
Yeah, I was gonna say, stuff we were working on, some stuff when, like just before we started.
That was very cool.
Trying to get Anthony's decision.
Not that we're one, so.
But you gotta, yeah.
Did I get on first?
Good, I get it. Control.
Is there anything that I can't see up there that you guys did?
That was like
Okay.
six-
Nope, that's it.
That was the 6 points for me.
You got more colors.
Yes, but 6 points out
Cool.
of the 60. So it wasn't 6 points out of the 40.
Oh,
It wasn't 30
I
minutes.
think it came out like.
So we had an hour, but he gave us 30 minutes, thank you, man.
It was kind of nice though, you didn't have to do like a ton of math. It was more like, you know it, you're good. If you don't know it, sucks to be.
yeah, good time in that. It's been the worst part of this whole degree.
It takes me like 5 minutes just to figure out what one that I can do and how to use it. Let alone solve it.
Just to go through the
some of them we get a hard time. And so sometimes it's even if you get it wrong, it's what and stick it on some. Well, she's just gonna post an intake from the passport, and you have to go look for it.
It's actually a high school thing. That is great.
That's for did you register? This morning. Yeah, I don't do it because 452, 1 to 3 kids when they get here. You're gonna end up being in that. I don't know. But I know he's having 2 of them again. The first one is almost fills up like pretty quick. So I think this quarter, even though we have like 4 people at each station, but just looking at the relays, I think there's only 1 or 2 of them.
Oh, that was not the right thing. Much better. Okay. Don't mind me dealing with questionable drivers for my drawing tablet. By default, so I have 2 screens set up. By default, my drawing tablet maps the tablet to the entire 2 monitor space, so it just like flies horizontally. So I like go in Linux, I can go and change it and be like, no, I only want it on this one screen. So that's what I was doing. So I'm going to get to this in a minute. Let's see. I think Timber's up, and then as soon as Timber comes back, I think we're all here. Okay, so I think everybody's back now. I'm just going to move this off to the side a little bit. The way they drew this symbol, it's kind of huge. It takes up most of the sheet. And we need to do that power circuit that provides this 3 volts for our chip. So this is going to be like the first building block circuit that I'm going to talk about. It's chip designers, when they go and make the chips that they want to sell, their goal is to make it as simple as possible. They don't want everybody to have to go and do super complex analysis to use their chip, because the harder it is to use, the fewer of them they're going to sell. So voltage regulators are one of those things that's really, really simple. So I'm going to go draw a box here where we're going to do this circuit. That's like 4th icon from the bottom and the right over here. So I'm just going to add a graphic line and just like partition off some space visually, because I'm talking about another circuit. I could even set up a hierarchical sheet, but they changed that in this version of KiCad, and when I went to use it earlier, I didn't know how to use it yet. Now I'm going to go put a little bit of text, and this is just so we're like telling ourselves, oh, this is the voltage regulator circuit. This is what I'm going to call it. So when you go read the schematic and you're like, well, what part of it's making this voltage? It's pretty easy to see. Oh, voltage regulator circuit, that's probably it. Well, we might resize this box later, but I'm just making a place that I'm planning to put this circuit in.
I was just looking at it, not a global.
Oh, that was text, not a label.
Okay.
So
Okay, underneath.
text was right next to the graphic line there. You can even add images and other stuff in here too if you wanted. Put your company logo and whatnot. And then I'm gonna go put in here, and because I happen to have a reel of these that we can use, I'm gonna put in the AMS 1117, or let's see, AMS 1117 3.3. So the 3.3 volt version of this, and I'll explain that in a minute. So I'll leave this up so everybody can see what the name is. And this is like the, people call them jelly bean components because they're just like really common, they're really cheap, and tons of different companies make their own version. There's like the LM1117 and the TI1117. So a bunch of different companies have this part that's interchangeable, and I have some from like a sketchy Chinese supplier. I have a reel of them. So we can use those for this. So the AMS 1117, the 3.3 volt version, and as you can see, it's a highly complicated device. Is there anybody here who wants to guess what VI means? Yes, can you guess what VO means? And what do you think GND means? So that's pretty much the gist of it. We go and put a ground over here, and then we want our 3 volt out, so we're going to do our V3V3 label here for the output. And then our voltage input that we're going to get from this, if we assume we're powering our board over USB, is going to come from the USB. And, oh, I don't remember what it's actually going to be called here, so I'm just going to call it USB VDD. Yeah, you can just duplicate the labels, and that actually makes it so you don't make any mistakes with them. Like typing, like I almost made my V here lowercase, and I think they're case sensitive, so. I don't have them connected yet because we actually do need, so they are going to be connected, but we are going to need some additional stuff in this circuit though. So I'm just going to try and leave this visible here for everybody to catch up, but when we go and I pulled up the data sheet for this so we can see what it is. If I can, it wants to hide from us all on the right. There we go. So you can see this is a 1 amp low dropout voltage regulator. So a low dropout voltage regulator, or a linear voltage regulator in this case, it takes a voltage at the input. Oops. It takes a voltage at the input and then makes sure you get the right voltage at the output. And it's linear because it's not using, or I'm trying to think of the best way to describe this. It doesn't do anything super fancy. It literally goes and takes, if you have 5 volts and you drew power at 5 volts, or like you drew 1 amp at 5 volts, you're going to use 5 watts. In a voltage regulator, if you draw 1 amp at 3.3 volts on the far end, you're still going to use 5 watts, and the leftover 2.7 volts worth of the voltage there dissipates 2.7 watts in your voltage regulator. So they're not very efficient. So they literally they're like, well, if you had 10 volts and you needed 5 volts, it's going to throw away half the power and just burn it off as heat.
So it's doing like a voltage division.
So yeah, it's literally, it uses transistors and so on inside of it, but ultimately they act like resistors in a way that just vary as needed to ensure that the right amount of voltage ends up being dropped across it. So these linear voltage regulators are super simple, super easy to set up, great for when you have very low power that you're going to use from their output, but they are really bad for anything that you need to draw a lot of current from. So you'll actually see, they're very clean power though. So everything's a trade-off. The linear voltage regulators usually give the cleanest power out of everything because they're not like going and doing what switching regulators do and make it noisy or anything. You'll see in a lot of like audiophile equipment, they'll go and advertise that it's a linear regulator, and they'll have a massive heat sink on it to dissipate the power, because it does create create less noise in the circuit. So they're a pretty safe choice for when you're able to fit like that into your power budget. And then for us, like a microcontroller only draws tens of milliamps at most. Like, I don't know what it is off the top of my head for the Raspberry Pi 2040, but the Arduino is like 30 milliamps maximum. So we're throwing away milliwatts of power with it. So there's no reason to get all fancy with the power for our microcontroller. Actually, the Pico board itself does use a more complicated regulator than this, but we don't need to worry about this very second. So the other things you need with this regulator, and it's going to tell us in the data sheet. Oh, there it is. So I will say, it says 1 amp. Do not ever pull 1 amp from one of these, because that is one. I jokingly say that's 1 amp if you submerge it in liquid nitrogen. So it's saying like the silicon can handle 1 amp if you can get rid of the heat created. So that's like a hard limit. Like at this point, it physically can't operate, but you have to overspec these things because it's like rather optimistic, because there's a certain limit to how much power you can actually dissipate. So if I go and it's somewhere in the data sheet in here, it'll say like
Safe operating.
Yeah, or even absolute maximum. It'll tell you how much power you can, see, power dissipation, turn it. So it looks like this one will actually turn off if it's too much. They tell you how hot it's going to get based on how much power you're trying to dissipate. But like anything over like half a watt in these, I know from experience you're going to have trouble with. And half a watt comes up way faster than 1 amp does. So anyways, we go and get here. This is trying to find their example circuit. So again, they just have example circuits in here. They show you how to use the chip. Let's see. So this is for the adjustable version. You can get versions that do an arbitrary voltage. But we're not going to be worried about protection diodes, but that is something you would want for ESD. They don't have, okay, so they have example circuits, but only for the complicated ones. It's also going to tell you, so they want on the output here, if I can zoom in on that, they say they want a 22 microfarad capacitor on the output. So the voltage regulator is pretty great, but it helps it a lot if you have a capacitor on there for it to store the power that or to store the voltage that it outputs. So we're going to go and add that. Yeah, no, I'm not going to worry about the protection diode. It'll work without it. And so we're going to go put that in. I have some 10 microfarad 0805 capacitors. So we're going to use 2 of those instead, because I have a reel of those. And you'll actually find that that's really common in a board. You'll see like a component duplicated because they didn't want to have to include. If you have a 1K resistor and you need 2K resistance somewhere, when the manufacturers actually put boards together, it costs money the more different types of components you have. It can be better to put just 2 of a 1K resistor in series instead of having a whole new part number. So for everyone who's not an E major that knows off the top of their head, if you put 2 capacitors in parallel, you just add their capacitances. And capacitors have humongous tolerances, like plus or minus 20%. So it's not that big of a deal if we just have 2 10 microfarad capacitors instead of a single 22 microfarad capacitor. So I'm just going to say 10 UF or 10U and do 0805 again. Hand soldering. Duplicate. I'm going to move the text around here. Actually, that's probably fine. I'm just going to use G to drag this flag over. And then somewhere in that data sheet, although I'm not going to go and hunt for it right now, it probably tells you and appropriate input capacitance, but it doesn't specify what that is. But usually you just end up using the same on the input as the output. So we're gonna just duplicate this and put it on the other side. Then maybe instead of duplicating all these grounds, I'm just gonna do a single ground and attach it to everything. Basically, every project you do with a microcontroller is gonna have this circuit or something that does the same thing in it. So that's why I consider it like the first building block you should probably have. How do you get a voltage that you need when you don't have it right away? And I'm just gonna compact this down a little bit, keep some information density on our sheet. I'm using G to grab these and shrink it down. So okay, here's our little like voltage regulator circuit. Nice and boxed over in the corner. I'm gonna go and draw the USB circuit because there's nothing interesting about it. I'm not really gonna talk about it. I'm just gonna put it down real quick. And I'm looking and trying to find a USB connector, but I haven't found a perfect one yet, so I might tell you guys which one to use later, but we can probably map this later. So, mini or micro, oh my god, which is it?
You like mini?
You like mini?
I like them all.
Okay.
C's preferred now.
Yeah, so the USB-C, and actually we were just over this because Justin tried to do a circuit board design with the USB-C. Those are really, really hard to solder, we discovered.
Yeah, no,
I did it under a microscope and like still had to go in under the microscope, use an X-Acto knife to remove solder bridges. You have to have like the perfect amount of solder because the pitch is so small on like, because there's so many pins on a USB-C and it's so small.
Is that on a hot plate or an air gun?
So it was with hot air. And yeah.
Let the manufacturer do that.
Yeah, it's not a big deal if you have a manufacturer that does it, but honestly, when you get like tighter density, you're probably going to end up paying more for things though. Like you definitely pay a premium for like ball grid array components, which are like, instead of having like a bunch of pins on the outside, they have all these balls underneath. They're great for like high density, but then they're really hard to solder by hand, and they're even harder to solder provably right by hand. Or you cannot solder them provably right by hand. So it's just a little diversion there. So okay, I'm gonna actually change the name of this label to VBus, because that's what it's called on this, just to be consistent. And I'm just gonna stick flags according to what it was. DP is data plus, DM is data minus. Shield gets connected to ground. And actually I don't know what ID is off the top of my head. Is that like to identify host versus like device or something?
So like if something's plugged in.
Yeah, I'm gonna look it up real quick. Oh, so that's for USB on the go. That's why I haven't seen it before. Okay.
So what's ID?
So ID is for USB on the go.
On the go.
So USB used to be like strictly host to device, and USB on the go is trying to make it bidirectional.
Basically.
What was that?
We go reverse instead.
Yeah, so basically to indicate like it can be both ways. So I'm gonna actually just look at what I have I'm kind of cheating in the corner here. I have the Raspberry Pi schematic, and I'm just gonna look at what they did for that one. If I can find the USB connection, where is it? There it is. I'm gonna guess.
It's 4, so they didn't do anything.
Yeah. Okay. So they didn't connect it. Sounds good to me. Don't worry about that pin. By the way, It's really hard to tell what these pins are, and whatever this they did not do this in KiCad, and whatever software they did just put pin numbers.
Yeah.
That is terrible. So I'm just going to leave that in the corner. I don't know. I might combine that with something else in another block later.
Where'd you get the VBus from?
VBus. So
You changed the USB, what was it, like USB VDD.
yeah, I changed it to VBus to match what it is called on this symbol.
I like it, thanks.
Just so I try to, you don't want a bunch of different names that mean the same thing floating around. So it's sort of you like try to leave breadcrumbs for yourself when you come back to design in a week and you don't remember anything. You're like, so is USB VDD the same as VBus? Is it? Now you have to go check, or you made them the same name and it's not a question that comes up.
Do we need to put pin 4 as a no connect?
Yeah, thank you for saying that. Because when we run the design rules, it'll complain if a pin's not connected. So there's this little, on the far right hand side here, there's a little X right here, no connect flag. So you just want to click that, and it's this little X and goes on there and says, we're not going to connect this anything, don't complain about it. It's right here.
Okay.
This button gives you no connect. And you can just place it on the pin. So let's see. I think the last thing I'm going to add for the moment before we hop over and actually start the circuit board is the crystal. I put the ground on the bottom of the microcontroller real quick, so don't forget to do that. These are probably all also shared pins. And I'm going to place component xtal, probably, or crystal. I don't know what it's going to be called. I'm just looking for a symbol. There, crystal small sounds good to me. I didn't set a footprint for the USB yet because I don't have the exact connector yet. And I'm going to have to look at which ones are going to be available that we can use. So we'll have to come back to that, but we have the schematic drawn for it. So it comes in from the USB, we do our voltage regulator circuit, and then it powers our thing.
So you just added ground and crystal small, right?
Yeah, so I just added ground and then crystal small.
Okay.
And I'm looking up very quickly in my other screen here what value we need for that crystal.
So what does the crystal do? What will the
So the
This one has
so yeah, I think there's actually a Falstad simulation that looks really nice for what the crystal does.
USB.
I think, I'm not positive. Just give me a moment to look while everybody catches up.
So the
I was like copying.
the chip requires a 5-volt line to it, right?
I believe the chip requires a 3.3 volt line to it.
Yeah, but USB VDD, that's 5 volt.
Yes, that is 5 volt.
That's why we have the voltage regulator.
Yeah, so that's the voltage regulator. So if you go on the screen here, so we're taking in the 5 volts from USB. So USB is 5 volts to VBus. We're going to our voltage regulator circuit, and we're going to connect that VBus through this voltage regulator.
Okay.
And we get our 3 volt output. And then over on our chip, we have our 3 volt input.
Yeah, but on 49, the USB D, that's just tapping into the 5 volt line, right?
Oh, yes, that does require that. Sorry. Yeah, because it needs the 5 volts to talk on USB. Thank you for bringing that up, because I completely forgot I put that there. And actually, I need to change that to VBus.
Nice.
Good catch. So if anybody didn't see that, change the USB underscore VDD to VBus to match these 3.
move it like to this, yeah, and I don't know how to do this, but yeah, I think I can do this.
Okay. So here, to answer the question, what does the crystal actually do? This is one of those like circuits that to me is kind of black magic right now. But I can tell you, basically the crystal, when you go and apply a voltage to it, my understanding is, when you apply a voltage to the crystal, it actually like physically distorts the crystal structure a little bit. And then when you you apply a voltage to it, it distorts the crystal structure. And then when you let go, the crystal wants to go bounce back to its other shape, and it will actually sort of ring at a particular frequency that crystal is tuned for. And then the challenge is creating a circuit that uses that property to, and it's very precise. It's like a very precise frequency it does it at. So the challenge is creating a circuit that uses that to create a clock out of it. So this example here has this. It's not a square wave, but then you would turn this into a square wave. It's an analog circuit. It's not something you need to concern yourself with how it works, but it's just that's what it's using it for in there.
Okay.
And ultimately, it's going to boil down to we have a crystal that we're going to attach to our microcontroller, and then it needs 2 loading capacitors on it, which are specified with the crystal. So as soon as I find where they put the crystal in this, I'm going to say we're going to pick one the same size as the people already figured it out. And Raspberry Pi actually has like a big sheet on how to design a board for the RP2040, and they explain how to pick a crystal for it and give you suggestions. We're just going to copy what the Pico does for the moment.
What does the crystal does?
What was that?
What does the crystal do?
So the crystal's the clock source. So the let's see. I'm trying to figure out what level to pull back to explain it. So it's the clock source. So every time a clock happens, the processor, the microprocessor, advances its state, right? And you want it to advance its state at a regular rate. And you want to make sure it's all synchronized and everything changes at the same time. So you don't have just something that's chaos.
It's kind of like a really fast second-hand potential.
Yeah,
It's
so
just saying this much time has passed, basically. Do something else.
There's a timer,
Yeah.
kind of like a timer for the board.
so
It's a way to keep track of time. So, for example,
That's pretty cool.
So, like what I've pulled up here is a counter that uses a clock. Your microcontrollers all have timers in them that do literally this exact same thing. And they take a clock as an input to it. So this thing's supposed to count up every time. And, oops, I connected that to something wrong.
the silver. Yeah, and so what it does is it's sending a 16 megabit signal. And so that means that it's ticking 16 million times a second. And that allows us to go ahead and say, okay, we'll count how many times that's ticking, and we can have a set understanding as how much time. So if I wanted to say, okay, set a delay for a second, I'm going to count the clock ratio.
What was the name of the crystal circuit?
Oh, in Falstad?
Yeah, so
That was in,
it's a microprocessor, so it's one of
that was under circuits, transistors,
we're connecting up to all the little stuff.
oscillators, crystal oscillator.
Oh, thank you.
Yeah, just go and poke around it. Falstad's great for visualizing things. I love the way it shows you the voltage with the color and the currents flowing. So it's great to get an intuitive sense. Okay, at a glance, I don't understand how this whole circuit's working, and I would have to sit down and crunch numbers for ages to look at it. But I can just go and put it in here and see what's going on. And I can even go and tweak values and be like, what if this capacitor doesn't match? What happens? Oh, well, it doesn't look too happy anymore. The biasing's wrong on the transistor. So you can break things quickly and see what happens also. Yeah, exactly. Okay, so right. Oh, why is it not zoom? There we go. So it looks like the crystal circuit that we have to do for the RP2040 looks like this. So let's set this to a 12 megahertz crystal. And for the footprint, most of these I believe are 5 millimeter leads. So I'm going to find a 5 millimeter crystal. But this is something probably we'll have to change when I find the crystals we can actually use to build these. See, I don't want surface mount, I just want a through hole one. I guess it's 5.08. So I'm pretty certain this will be the one, the size that we'll get to do these, but we might have to change this later. On the crystal, choose the resonator 2-pin W 6 millimeter.
Resonator 2 H3. Yeah.
H3, yeah.
2 pin W6.
So it's going to be a vertical mount.
No, it's through hole.
Oh, I know. I'm just saying that the crystal oscillator is going to be mounted vertically. Restrictions to constraint.
Yeah.
For the record.
Yeah, it's like a little metal can. It's not that
Yeah.
tall. These are also like the easiest ones to solder. So, if you didn't find the exact one, don't worry about it at the moment because, like I said, there's a chance we have to change it anyways. So let's hit OK on that and put in the rest of the components for this. So it looks like 2 more capacitors. And those are 15 picofarads or 15p. And we're going to go with the same 0805 footprint because those are easy to solder relatively.
C small.
Yep, C small thing and then the 0805.
It should come up in your recent.
Yeah. 15. Oh, 15 pico.
Yeah.
Yeah, they're very, very small capacitance values.
So when we are like doing all this thing while reading it online on this computer, when you make it on the motherboard, does it like or the board that we are using in physical state, so it stores all these values?
So the value that we enter in here is more for our reference, so we know what the correct component to pick is in the schematic. When we go and build it, we would actually go and, so let me back up. When you like send it to the manufacturer, if they're putting the components on for you, those values matter. They actually show up in the like bill of materials that says.
So we are just basically making a handout of the board.
The design.
Yeah, so we're gonna, so what we are planning to do is we're gonna make this, we have to design the schematic first for the board, and then we're gonna actually make the like design for the board itself and put those together. So we're gonna send them out to a manufacturer that's actually gonna make them. And we're not going to do their assembly service because it costs more money than we can really afford to do for the workshop. So it's going to probably be me soldering on the hard to solder components for everyone, and then everybody can solder everything else. Particularly the microcontroller is really hard to get right because it has no leads on it. But if you were, and I'll show probably in the next workshop how to do the outputs if you were going to have them place the components for you. But it's a convoluted process, which is why I don't want to do it like up front. Probably I'll show and not ask everybody to follow through, so that you could be like go back to the video later for it. because I've done it. I've had them like place the components for me, and it's like not straightforward because there's not actually a standard like way to do it. So they actually have, so this is a different circuit than probably we want to use. So I think I'm gonna, for the moment, go with a simple circuit. I apologize to everybody who may have
Yes.
done something more to that.
So basically,
If we need this more complicated circuit that they have, then maybe we need to, but usually a lot of this circuitry is built in, and what they're trying to do is a different type of resonator. So I'm just going to ignore this, connect it like this, and I will correct later if we need to do that other circuit. By the way, the 12 megahertz crystal is chosen on this, I guarantee you, because USB is at 48 megahertz, which is an even multiple of the 12 megahertz. So they need a 12 megahertz reference.
what does X in mean here?
Crystalline. So X usually is used for, it's like either X or Y are usually the letters you find associated with crystals. So yeah, I guess you can see how like X crosses, so crystal. Or X-Tal. I want to go on to another building block circuit, which is an LED, so a light to light up on our board. We want some sort of status LED to let us know, so we can blink it on and off to know the board's actually running or something. And there are a few different ways to do this. So like a super basic LED setup is going to be pretty easy. I'm going to go make another box over here that I'm going to put this circuit in. We could probably do it off the board also, but I'm going to make a label that's, let's see, power LED, PWR LED. So we know this is the input to it. And then I'm actually going to hop over to Falstad to show why we have to design the circuit the particular way we do. So is actually just barely there. Okay, so what I have here, this is the LED. It stands for light emitting diode. It only allows power to go, or current to flow in one direction, is the simple way to describe it. And we usually want it pointed to ground, like this. So we provide the power from our microcontroller. I'm going to add a little switch here to show. So what the microcontroller is going to do is switch on and off the LED. And this, you can't really tell here, but this is shown as actually kind of dim because it can just barely turn on the LED like that. We have to have a resistor in here because the LED, once you've gone over the voltage it needs, conducts way too much current and would potentially damage your microcontroller. So like if I take this resistor out and just make this a wire and just connect it straight to the LED, the simulation I think will actually, well, it's not going to error out, but it's saying we're putting 18 amps through it, which is way, way too much. These are usually 10 milliamps or 5 milliamps for small surface mount ones. So the way you would find out normally is by looking up the data sheet. It will tell you what the voltage drop will be at the rated power. So usually this would be like 2.2 volts for a red LED is pretty common. This one, this default LED, we can actually see what it's going to try and make the drop. So this LED actually, well, I guess it's the whole thing, it has to be. So you would just go and if you had, say, a 5 volt source and it was 10 milliamps at 2.5 volts, then you would go and calculate your resistor value as if you were just doing a resistor with 2.5 volt supply, and that gets you close enough. The actual calculations are more complicated, but like usually something around like 200 to 1,000 ohms is fine for connecting from your microcontroller.
It's the formula, the voltage minus voltage drop
Divided by your resistance. Yeah. And then I guess I should show that real quick. I'm trying not to do too much like circuits because I also wanted this to be open to CS, but I guess that's, so we have like our voltage source here that's going to get connected. The microcontroller takes the place of a switch and it's going to get connected. We need a resistor and the LED. The basic like model of this goes and says replace this LED with a voltage source of whatever drop it's going to be. So for a red LED, it's like 2.2 volts. For a white LED, they're like 2.9 to 3 volts. You have to look it up for the one you have. And then we go and like calculate a loop here, and then we go and say, so if this is whatever VN, this is VD for V diode, then we want to do, at that point it'll just be Ohm's law, so it'll be VN minus VD divided by R equals our current. We want 10 milliamps usually, so we do 10 MA and solve this equation. So we just multiply by the resistor, divide by 10 milliamps, and that'll tell us what value we actually need. I will say though, don't do 10 milliamps from the microcontroller unless you check that it's okay. A lot of them, like I'm pretty sure there are multiple pins on the STM32s I've used that are like 0.5 milliamp drive only. So I'm going to get to another circuit in a second as to why. So aiming high on the resistance to make sure the current doesn't become an issue is not such a bad thing to do here. And I'm just going to go and say, let's do 470 ohms. That'll work. It will be within spec for any LED we would use here. So I'm just going to go and put R small. And an LED. And a ground. Now let's duplicate this ground over here. Timber, as a computer science student, do you feel lost with that description or no?
I did circuits recently.
Oh, okay.
So,
So you don't count, is what you're
Yeah.
saying. David, you jumped in halfway. Did that lose you? I want to know.
I was working on something else.
Oh, well, I appreciate that.
I'm sorry.
No, you're good.
Well, I was trying to follow along with the symbol, with the diagram thing, but I couldn't find the symbol for the part I need.
Oh, okay.
So you might did the same wall that I did with the RP.
Are you trying to do the RP 2040 or your different project?
The other project.
The other project. Okay.
Yeah.
You might have to make a symbol for your thing if it's not in there.
There's like 140 pins. I don't want to do it.
If it's sold by Mauser, go to Mauser and say you want to buy some, and they will make the symbol for you. And be like, well, I'm still working on the design. I'm not going to order them yet, but you have to have the symbol to make the design. So you go and request a symbol, they'll make it for you.
Seriously?
Yes, they will. There's even a button on the website.
Oh my god.
So there's like a button that's like request ECAD symbols, and they will make it for you. I haven't done it, but I'm pretty sure they don't charge. That's something like, as soon as somebody needs it, they're like, we'll make it because it's going to help us sell them. So why not? So the thing I mentioned earlier with not being able to provide much power out of your microcontroller to power an LED, like even just driving an LED 10 milliamps puts, like the Arduino can only drive like 3 LEDs at that in ideal situations before you risk damaging the outputs. So I'm going to show you guys how to use a transistor as a switch to control your LEDs. So it's like a very simple circuit, but it's something that you don't get shown until you're like in microelectronics 2 maybe. And I think it's kind of a tragedy because it's just so useful of a circuit to know how to do. So if instead we had, so this is the input from our microcontroller at 3.3 volts here. I'm going to instead make this a 10 kilo ohm resistor. Or actually, let's do a 5K or 5.6 because that's a standard size. And put in an NPN transistor here. Put in my ground. Put in my, that's a diode, let's do my LED. And then the other advantage to this is we can actually use the power from the 5 volt USB bus instead of our regulated output in this circuit. So I'm going to put in 5 volts, oh, wrong thing, put in 5 volts. So you can sort of see there's barely any current flowing right here with the little dots. But over here, there's a ton of current flowing through this LED right now. We still need, and we still should have, a resistor for the LED, according to what we want. So we were saying 470, but now that we're not driving it directly from the MCU, we can do 220 ohms. And, okay, it looks like that's just a little bit high at 5 volts. So I'm going to do 330. There we go. That's another standard size. It's right about 10 milliamps for this fake diode. If it was a white one, probably we would want the 220 ohms, and if it was a red one with like 1.7, we're going to need a different value. You have to look at the data sheet to find out what you need. Going a larger value is just going to make your LED dimmer. Going too low will burn it out. So you can see we're drawing 472 microamps from our microcontroller. Here I like hovered over it and it shows you in the bottom right what it is. But then we're pushing 9.5 milliamps through our diode here, or through our LED. So we're able to light it up and it doesn't consume power, 1 from our regulator or 2 from our microcontroller. So if you're going to be lighting more than a couple LEDs, you really ought to do this circuit. So let's just go and add one of those in here, and I'm going to try and leave this in the corner so it's visible while I do that. Yes, I highly recommend playing with Falstat at some point because it's free and it makes it really easy to get an intuitive understanding. So let's see, I'm going to need the VBus label here. Oh, I never set a footprint for the LED. Let's get in there and do that right now. I went back to the last circuit, the LED, because I'm going to copy the symbol. What was that? I didn't do the resistor either. We should add that in. Yeah. And if we leave one undone, it'll totally tell us later when we go to add it actually. So it tries to be helpful like that. The very common LEDs that you get in like a package for hand soldering are these 5mm LEDs. So most of them are either, we like have a bin of them. Yeah, most of them are either 5 or 3mm for the through-hole ones. So these are 3mm. If anybody wants to see them, they can come over here and look at the bin. Or yeah, exactly. The common, these are 3mm. The slightly larger ones are the 5mm. And then you have 10 millimeter RGB ones.
Also for later workshop, we're gonna work on our own project, right? So if you wanna include your LED design in here, you can.
Yeah, like if you
consider
wanted to,
those
if you
steps.
were like, if somebody was like, I want to go and design a Christmas tree and I don't need a microcontroller for that, or even if you did want a microcontroller for it, perfect. That's great. Actually, somebody should do a Christmas. Now, you should do a Christmas tree for our soldering workshop.
Yep.
And use a microcontroller and RGB LEDs. That would be awesome. Have like RGB ornament lights on it.
Yeah.
That would be a perfect use of this workshop.
Yeah. I think the next one.
And
would
you
be
need to
a
use this circuit
Easter
also.
theme, Yeah.
Or Eastern theme. Make an eagle with glowing eyes.
Yeah. And then we can do like fundraising and all stuff.
So,
Control rated.
the SMD LEDs, I think actually I would consider doing an SMD LED for something like that power button. So I'm actually going to grab this, let's do the 1210. So if you look, this 1206 right here, footprint is skinnier than this 1210 footprint. I don't know which one I'll get, and I'm just going to go with the 1210 because I know it's going to work with any LED I would put down. And that was under LED SMD.
You want the hand solder version?
On this particular thing, actually, I'm not going to do the hand solder version.
Why?
Why? Because when I've tried to solder LED, so one disadvantage to the hand solder version is because it has a bigger pad, they'll solder and make a good connection, but be kind of crooked, right? Which doesn't matter if it's a resistor, but if it's an LED, you'll notice if it's crooked. So I'm not going to do the hand solder on those, even though it's harder to solder.
It's going to be the same thing, it's just you're choosing the pad.
Yeah, so the hand solder version just have larger pads to make it easier to like get a soldering iron on them.
Okay.
And the like ones for the manufacturer or like like automated install
Precision.
are like they have just the pad's only slightly bigger than the component you're putting on there. So there's not really that much room to move around.
That makes sense.
So let's see, I'm doing that. I'm gonna go. Actually, wow, time has. Everybody's been much more quiet this time, and I didn't realize how fast time was going by.
Because we don't have to learn.
I'm gonna go and set the footprint for the resistor because I actually wanted to talk about how to set up all of our layers on the circuit board. So I think actually because I want to get to talk about all the layers on the circuit board, I'm gonna jump to that now. And you guys saw this circuit here is the one you would have to design in.
Just put the NPN transistor just to get
Okay,
a footprint for it.
I can do that. We don't know which NPN we're gonna use though. I have a very. It's the we're going to use either the MMBT. All right, it's SOT 23 anyways. So let's see. Here, no, that's not what I want. I'm going to look up NPN. Yeah, let's see. So you see the NPN symbols. There's a bunch of different versions of these here, and it's because the pin numbers are different for different packages. You see as I click them, it goes through. So you might have to change which schematic symbol. Actually, I wonder if they have the one I have. Oh, they do. They do. Okay. So I have like 4 reels of 10,000 of the MMBT 3904, and I think I paid like $20 for all of them. So these are cheap. So do the MMBT 3904 because I have those. And I'm going to put it down, but I do want to get to the.
Thank you.
So anyway, that's the one right there to do that. So it's going to give us some errors when we jump over because not everything's all connected yet, but that's fine. We have to annotate. I'll remind everyone you have to annotate before you jump over. So I'm going to click at the very top there. It's called Fill Symbol Reference Designators. You click that, it pops this up. The default set, I'm going to put the corner right next to the button. Default settings are fine. I'm going to click Annotate. And it goes and does it. And just a reminder, what that does is it goes and renames all the components and gives them individual numbers according to. It actually goes like left to right and top to bottom to give them numbers.
All the question marks.
Yeah, it replaces all. So instead of saying C question mark, it says C1. And then I'm going to go to Open in PCB Editor in the top right here. and then I'm going to do update PCB with changes from schematic, which is sort of top center here. And Chad, I'm sorry, I remember you had to go through like the whole net list thing because the button's literally not visible on yours.
I remember having it.
Okay, good. So you see when I went to update, it's giving me errors here because there's a component that doesn't have a footprint assigned yet. So it will give you a warning or an error here when there's something questionable like that. Remember that this is here because when you do your import is the only time it will remind you there's no symbol for it. And then I'm gonna go and plop this down over here. Before I start fussing with these, what I did last time for our like pre-set up, let's go modify this, is I already set up all the layers for the circuit board. So, and this was actually the reason I grabbed this in the first place. A circuit board is sort of anatomy of a circuit board here. We have what are called copper layers. We have like a layer of copper, and then we have a layer of substrate, which is usually fiberglass, in between layers, which is much, much thicker than the copper layers. Let's see. And then, so if this was just a 2-layer printed circuit board, this is more or less what you're looking at. Is you have, I know this is awesome graphics here. You have a copper layer, a layer of substrate, and then another copper layer. And there are circuit boards, modern circuit boards, that have as many as 16 layers of copper sandwiched in between these, right? So if I go and, again, my awesome graphics here. We're going to do 2-layer boards, but if you had a 4-layer board, you would have sort of like this, and you have to go and specify. JLC PCB, which is where we're going to order from, they have a standard, and they're going to tell you what it is, and they do it for such a low cost. Unless you do their like advanced thing, you can't specify these, but we should tell KiCad what they are. And that's going to be how thick is this layer of copper, how thick is this layer of substrate, how thick is this layer of copper here, how thick is this substrate throughout, so we know. So very commonly you'll have what's referred to as 2-ounce copper, which is like there's 2 ounces weight-wise of copper per some area. And then you'll have ½ ounce on the inside, but there are other options besides that. That's what JLC PCB uses, and it is the most common that you'll see around. So we have to set that up, and then that's the like layers of the physical board, but when we go and set it up in KiCad, we have all these other layers that are part of our design. So I'm going to go, and in the top left here, there's edit board setup, including layers, design rules, and various defaults. And every time you go do a project, set these first, because if you change them afterwards, everything is going to be screwed up. Because this is what lets the design tool actually help you and show you how to make good, the right decisions and put things where they're supposed to be. So,
how did you get there?
So in the top left here, there's this little picture of a circuit board with a gear.
Oh,
Click
it's
that.
on your mouse. It's on the top left.
Yeah, I know. I was like, I came here early to figure out the mouse issue, and I was like, oh, the mouse is showing, it's fine.
Yeah.
And then I discovered as soon as I clicked out of the like software, it hides it.
Yeah.
So that's great. So when you have this up, we don't need all of these layers for what we're doing because some of them are things we're not using. So to explain really quickly, this is by default set up for 2 layers and tries to give you a sort of reasonable set of the, so I want to make sure I'm clear. There's like the layers of like a physical board, and then there's layers like in the CAD software that describe other things to do with the board. So, and here it says like off board or on board. So there's something that's just for the CAD software, and then there's something that's actually going to be physical. So courtyard, because you'll see this, we're going to leave that on. Actually, it doesn't let us turn it off. The courtyard of a component, when the footprints are made, says nothing is allowed inside of this space that the courtyard is because the component is physically there. Or it needs this space here because there's a pin. So the courtyard just lets it automatically go and say, hey, the courtyard of two components are overlapping. You're not going to be able to install them on the board because they're going to touch each other. So that's what the courtyard's for. The f.fab is the front fabrication layer. This is literally for notes for like the board house to go and say, oh, this component, such and such special thing with this. This is literally to draw text on, to like tell them stuff. And if we're sending it to a Chinese manufacturer that's doing it for $5, not only won't they read it, they can't if they wanted to probably. If we go and put text in on our own. So we don't need the fab layer at all. And if you look by default, it populates it with the name, like all the KiCad footprints, put the name of the footprint in the fabrication layer, which is just kind of messy in my opinion. So we're gonna turn that off. Then we have adhesive. So an additional thing, like in manufacturing circuit boards, you know, we think about we go and solder a component down to a board and that holds it there mechanically. But a lot of times components, particularly larger components, will additionally need glue to hold them down. Particularly like capacitors will have glue to provide additional mechanical strength. Because if your thing's like vibrating and you have like an electrolytic capacitor there, it'll move a little bit and eventually it'll work until it breaks a leg or something. So the adhesive layer is to say adhesive goes here for it. And you'll actually see, like when you look through data sheets of components, there will be components that will say, like actually USB connectors will say, oh, we need adhesive here underneath the connector. And that's actually part of the manufacturing process that's done automatically. There's not a person there with a glue dropper doing it. It's specified in here and they make like a stencil for it and white glue over the whole thing before they place the components. But we're not going to be using that, so we can turn that off. F-paste is the solder paste layer. So this is another thing for automation, which if we were planning to get these made automatically, we would want the paste layer for sure, but we're not going to get them made. So what the paste layer says is where we want solder paste on there. So
would it also be where you get the stencil?
Yes, and that is also for the stencil. So it's up to you if you want to leave it on. I'm going to just turn it off to make it clean when we look at it. So when you get so what he mentioned was they make what's called a stencil, which is like this stainless steel, like thin sheet of stainless steel that has cutouts on it. And those cutouts come from the paste layer. So they go and make a cutout for each little pad that's specified on the paste layer for where you need solder paste, which is like little tiny solder balls suspended in flux. So instead of like feeding solder on, they put paste down on everything. And that's the layer for specifying that. It's automatic in KiCad, by the way. You don't need to specify the paste layer unless you're doing something special. So you don't have to worry about it usually. I'm going to turn it off to keep it clean. So now we're into the ones that we actually need. Silk screen is like the white text that you see on circuit boards. And I actually don't know why it's called silk screen off the top of my head. But there are a number of different ways it's added, but it's the text on your board basically. So when you're going to put comments or show what your pinout is or put your logo on the board, you're going to put it in the silk screen layer. The F mask is the front side solder mask layer. So when you go and look at circuit boards, actually I wish I had something super handy to show. Do we have anything? So fiberglass is like a little bit green on its own, but it's not actually that green. The reason they're so green is because the solder mask is chosen, like you can choose different colors for solder mask. So when you're doing like your manufacturing, you choose different colors of solder mask. What are you shaking your head?
What are you talking about?
What? What, green's the only color for you or what?
No, sorry, I was just trying to distract you.
Okay, well you did, thank you.
Sorry.
So here, I don't need to see these. Hand these out to random people.
Yeah, pass it around.
So the solder mask does two things primarily. One, it covers up the like copper traces on the board, which keeps them protected from corrosion. And it also, when the soldering actually occurs on the board, it is really good about not letting solder touch it. So it will actually like bead up and not adhere to the solder mask. So it prevents solder from flowing places it's not supposed to. You'll see on like some really built down to the last dollar circuit boards, they don't put solder mask on them. And I recommend avoiding those. But yeah, the solder mask is actually a really important part of making a good assembly. So we're definitely going to leave that on. And then we have the front and back copper layers. So this is the actual layer of copper that we're designing our traces into on the board, on the front and back side, so F and B. And then we have all these things repeated for the back side, so we can go and turn off the backside adhesive, paste, and fab. And then I'm going to turn off all these user eco ones.
Turn off.
Turn off backside paste, adhesive, and fab.
Okay, V-paste, under V screen.
And then like turn off all the user ones, because these are like for your reference. If you're working at a design in the company and they say, hey, we need this information put here or whatever, then do it. But we don't need a million user things.
Turn on all the users.
And then there's some it won't let us turn off, and it makes sense why. Edge cuts is the like perimeter of our board, and then margin is like holes and whatnot that we're going to add to the board. Here it'll let us set the physical stack up. We don't need to worry about that. If we were doing multi-layer boards, like boards with 4 or more layers, we would want to go to JLC PCB and actually look at these, particularly because we're probably trying to calculate impedance and stuff on those. Let's see. In here, this is actually worth noting, under the board stack up here, the solder mask / paste, the solder mask clearance. So this is how far around a like pad or where a component attaches. It's how far to remove the solder mask around it. And questionable quality overseas manufacturers are known for modifying your files after you send them to them to increase the clearance so they don't accidentally put solder mask where it's not supposed to be. And yeah, so I'm just going to leave it at the default, but understand that if you're not going through like a really professional manufacturer, they're probably going to tweak it and not tell you. I've had boards made by like 4 different manufacturers, and I'm pretty sure that JLC PCB is the only one. I haven't seen JLC PCB adjust my solder mask, but they might have. Every other single one made it like huge. Like I would have a package down, and they would just remove the solder mask around all the pins in the package, so they were hard to solder to each other. Because it's hard for them to like leave like a little sliver in between the pins, so they're just like, we're not even going to try. We're not going to tell you. We're just not going to try, and make it anyway and take your money. So it does make it harder to solder. So just something about that.
So that's where you shrink it down so they do modify.
No, they're gonna just go and probably they have a software that automatically takes your design and does it. You can set the defaults for the text and stuff in here, but the other thing we have to do, and actually we're running out of time faster than I thought we were going to today, is we have this design rules. So this is like actually the really key part, because you can turn the layers on and off to show them or hide them or whatever. But the design rules here is the part you really have to set. So I'm going to go to jlcpcb.com, and up here at the top, and every like board house that's going to let you order like this is going to have this somewhere on their website. Capabilities. And most of them it actually opens when you click it, but I don't know. Okay, here we go. They'll tell you what they're actually able to do. And you need to set this in KiCad so that when you're designing the board, you don't violate the limits of what they say that they're capable of doing in their process. So they'll tell you all sorts of stuff in here, like the officially they'll do up to 20 layers now and all this blah blah blah. But we're paying attention to the 2-layer limits. So they'll tell you all these different tolerances, and the main ones that we're concerned with are the hole sizes and like the copper clearances. So I'm going to try and put that back up. If anybody needs to go and open up the JLC PCB website, I'm probably not going to go through the whole thing because we're shy on time to actually go through that. Where did my window go? Why did it go away? There we go. I'm going to set this to be above everything. There you go. Keep above others. And go back to KiCad. So, wait, wrong button. Why is this? Okay. Somehow I lost this. I don't know how. Okay. So in here, so actually it's not going to be in the drill holes, but we're looking at the minimum via size, and you're going to see minimum via diameter and so on. You just have to fill these all in here. So minimum through hole, this is set to 0.3, and we see that it's 0.2 here. We could go and adjust that to be 0.2. I don't recommend actually going down to the minimum. You want to stay away from it because they're like, this is the limit, this is the most we can do. The closer you get to that, the more likely it is that there's some sort of issue. So the 0.3 is fine, or you could change it. The minimum via diameter is 0.4 millimeters. It looks like that's already good. And somewhere in here they should tell us the minimum annular width. Or actually, it's just going to be calculated from that. So the minimum annular width, to explain it, I haven't explained what a via, have I explained what a via is yet?
Not yet.
Not yet. Okay. So we used one, but I was like, I'm going to explain it later. So now's a good time to explain it. So when you have my incredible drawing here of a circuit board, and you have these layers of copper on different levels in between the substrate, and you need to connect them to each other, we use what's called a via, or a vertical interconnect. So what a via does is it has what's called the annular ring, which is a bit of copper on the outside here, and then a piece that goes through to the other side that's that like through hole diameter and goes to the annular ring, and this actually makes like a conductive path between them. So they're like these little things, and if you go and look at any circuit board, pretty much you'll be able to look at them. I don't have the here, you could actually see that because I'm going to try and see if there's a good way to point out. You can see them really easily on the back of these circuit boards. What was that?
If you open up the file we worked on last time.
Well, I want to show them like actually on a physical thing. So at the end of like that trace there is a via. So right there, that's a via on the board. Like you see all these ends and then you get on them. So you see like this ends right here, that's what a via looks like on the board.
You can try to Google via PCB too. It has some good graphics on all those and different types.
So these are what the vias look like on the board. So that's
What was that next?
You can search via
So,
PCB
you know what they're
on Google,
like.
and they have some like diagrams and different types of vias. You can look up. So you when you run into any problems or like when you don't understand anything of the parameters and everything, like try to look them up on Google, and I think understanding them will help with the design.
Yeah. So like again, you're trying to understand what things are. There's a bit to vias. Vias aren't usually a failure point or anything, but we use them pretty prolifically on boards. There'll be very often many thousands on one design. So they do drill the hole. They like drill the hole and then they like put a little piece in there that's the conductive copper, and then they go and put the cap on it which is actually like part of the copper layer in there. I don't know the whole details of that process, and I was trying to find information on it, but I couldn't quite find how it works beyond that. I do know there's like options to like fill it with solder paste for more current capability and so on that are available out there. So there's actually, we could talk about vias for a half an hour and not have discussed everything about vias, but just so you know what it is, we're going to use them a lot, and we need to tell KiCad what we are allowed to do. So the minimum annular width is actually 1 millimeter or 0.1 millimeters, and the reason being the pad size, or sorry, not pad size, the minimum via hole size is 0.2 millimeters, and the minimum via diameter is 0.4. So the total diameter is the hole size plus the annular ring. So yeah, 0.1 times 2 gets us the difference in there. So that's just sort of quickly calculated from there. Minimum clearance in copper right here, and the minimum track width are important. So, oh, it's 4 o'clock. The screen turned off like last time.
Not on time.
Yeah. I need to remember and not go over next time.
BYOD.
No, it's not BYOD. It's the stream to it. It's the other option. There are two options, and BYOD is not the right one.
BYOD.
There we go. That's
Oh,
good.
it is.
It is?
Yeah, there's HBI and BR.
Oh, okay.
Yeah.
Sorry, Nat.
That's all right.
So let's see. I'm gonna look for in here. So like they talk about the minimum. So actually, I guess sorry. That was the minimum annular ring's 1.3 millimeters in the 1 ounce copper, which is what we're gonna use. Minimum clearances here. Let's see. Pad to pad. Via to track. So these are like the clearances of different things. So like a via to track, how far do those need to be away from each other? And it's not so fine grained in KiCad as it is over here. So we just want to say a minimum clearance that's at least what they specify in here. So probably we're going to want to do like this 0.33 millimeter for minimum clearance. You might need to go down if you're doing like a BGA or something that you don't have much clearance and really get down to these, but probably that's not going to be an issue for us. Minimum track width, so minimum trace width and spacing. So the spacing that they give for that, so that was for holes actually. I think that'll be fine. So it's 15 mil spacing. Minimum trace width is 5 mils or 0.127 millimeter. So that's going to be track width. I do not recommend using 5 mil traces. I recommend using 10 mil traces, at least for everything, unless you need the 5 mil traces, just because the smaller they are, the more likely there's an issue. So I have sent in designs that had a bunch of 5 mil traces and had them come back and say, hey, this is going to be hard for us to get a good yield on. There's going to be an extra charge. So again, stay away from the limits. I'm actually going to leave the minimum track width at the 0.2 millimeters in KiCad because I don't want to go down to their minimum. And the rest of this, like they actually tell you what the solder mask clearance needs to be in here and a bunch of stuff about that, but they probably fix it anyway. So that's all we need to set up here. Actually, the defaults in KiCad probably honestly have been tweaked to match these, so they don't need change too often. The only thing we had to do was increase the minimum annular width. That's the only thing we needed to do for sure. And then we want to set the predefined sizes in here. So when we go in through and make a track, we might have a few different like sizes we need to use. And like I said, I recommend doing 10 mil for like general tracks. So I'm just going to go add a track and say 10 mil in there. And then a more typical size for a via is going to be like 1 millimeter with a 0.5 millimeter hole. And you can add more if you need to. And then probably for power, I'm going to want to have 25 mil tracks. I'm going to add that in there. if you are going to use tracks of a particular size, it will let you edit them individually. The problem is if you need to change their size later, they're all like individual, and you have to change them all individually. If you put the size in here in a predefined size, you can change the predefined size later, and everything that uses that size will change with it. And then also there's net classes, so that's sort of the same thing. It goes and sets the defaults for the net class. So we would go in here, and actually I'm going to go and set track width to be 10 mil for the default net class, and I'm going to set 1 millimeter vias with a 0.5 millimeter hole for the default class, and then I'm going to add a power class and do those 25 mil tracks, and let's do 1.5 mil vias, and the via hole can stay the same on those. And we're pretty much done with the setup. This was like kind of the boring setup on here, but you have to do this beforehand so you have the software can help you do things well.
Big change.
I'll leave this up for a second. Dang, we're over time. I went slower today than I thought I was going to, because I actually had way more I wanted to do. But this is why I wanted to do 4 workshops instead of just one, because it's like I've been talking pretty much this entire time, and I hope everybody finds this useful, listening to me blab about this stuff. So
I don't find very much of this out.
yeah, I guess that's the point. Like try to share this stuff with you. That's like I can tell you, don't do 5 mils with JLC PCB. They'll complain about it because I've had it happen. So I did want to get to actually routing these though. When I go and accept it, it's going to let me know that I'm not going to be able to use the things that are in footprints that are part of layers I'm removing. That's perfectly fine because I'm not going to use paste or fab, so I'm going to just say yes. Now you see on the right, our layers are much cleaner. And yeah, so when we go and I don't want to go too much over, but I just want to say like on the designs here. So actually, I'm going to point out real quick. All these pins that are on this thing, this red circle that it shows around it is the solder mask removal. So that's what you're looking at, since I've talked about solder mask a lot today. When you're looking at, I wish you could see my mouse.
Yeah, we can see it.
You can see okay, you can see the crosshair now. So this right here is like the solder mask removal window. So it automatically removes solder masks inside of that with the default clearance. The reason I said I will probably solder these is because these pins are so close together and they don't have solder masks. They're really hard to get right. So like when I get the boards, I'll sit down and solder the controller on for all of you. Unless somebody really wants to do it themselves, that's fine too. But because these are going to be a bit harder to do. This is something where the automated manufacturing process can probably get it perfectly fine, but if you try to do it and you haven't done it before, you're probably going to just end up like frying a bunch of boards. Because that's what I did the first time I tried to do something like this, is I fried and stuff quite a bit trying to get it to actually work out. We will actually, if you want to have this as the start of your design, whatever thing you want to do, you guys can go and play with these later. So, and I actually really recommend going and do that, because I can show you stuff here, but really going and spending time with it yourself is what is going to help you learn how to use the software and do these. Like, you probably, like, I probably had like a third of the designs that I've done, particularly the ones toward the beginning. There will be something that's like a mistake that you have to fix by putting a wire on it later or something that sucks. And then there will be some things where you're like, I could have done this way and it would have been better, or I would have preferred to do that. Like my very first design, I did all 0402 resistors and capacitors, and I'm telling everybody to do 0805, which has 4 times the area. Those are so impossible to solder, and I just, I didn't understand how hard they were going to be to solder. I got them on, but I don't want to do that again. So it's just all these little things you have to learn by doing your design. So like do a design, don't worry about if something's wrong on it, like try to make something not wrong.
Yeah.
But then let's make it and then figure out what you want to do better next time. And then when you want to do your senior projects and make something, you'll actually have a few under your belt and be able to do something you really are proud of for your project. I should stop here because I'm already like 10 minutes over. But my very last thing to say is probably for all these capacitors on here, if you do F, it flips it to the back side of the board. Put these capacitors like right under the chip on the opposite side of the board and put them all there because there's a whole lot of them. That's exactly what you see in like professional designs. They'll go and put them on the back side underneath it.
Sprinkle them like candies.
Yeah, exactly. If you go and take like a computer processor like from AMD or Intel and you like, or like the older ones I guess I should say, and you flip it over, you'll see there's a whole bunch of capacitors there.
You'll still
That's
see
what they're
it.
doing.
If you have a motherboard on the backside of the socket, there's tons of capacitors right there.
Yeah, and that's just about it. It's a good place space-wise. It minimizes the distance that current has to go through them. And I feel like everyone should be able to, without too much difficulty, go ahead and connect all these components to this. You don't need to match what I've done exactly on this. In fact, everybody should do their own design. I'm just trying to give you circuits to use. So you know how to hook up an LED. You know how to hook up one that has a little bit more power. And I'll have to bring up a few other like circuits and things that we need to use with them at the next workshop. But my goal really is I would like to, next workshop, which is going to be in 2 weeks, I would like to show you guys the last bit of the circuits I want you to use. And then within a few days, if everyone can send me their design, then I can go over them and make the fabrication outputs and send them to the manufacturer for us. Which might sound like it's really close, but it's not. It's 2 weeks. I'm talking like in 3 weeks. Have something I can send. So this is most of what you need for this chip, and I'll go and post the Raspberry Pi design a circuit board for the Raspberry Pi manual that tells you all the pieces, and then think about what you want to do. Honestly, if you want to do a Christmas tree for, like I was telling Nat to do, that's great. If you want to include something else, then that's great too.
If this is your first design, do a small one first.
Honestly, put a few LEDs on there that you can turn on. Maybe put on a 7-segment display.
Like this is a simple one. It's just like a Christmas tree with like transistors and LEDs. So you can start out with something like this, and like after the first design, you can design your own, and then.
And then all the pins that you don't use, put them on the board as like a breakout, so you can use them in your project later. So you can have your Christmas tree drive an RC car if you want. Is there anybody who has any like particular questions they'd like to ask? And then I think we're officially done. I'm sorry for going over on this. Nobody like got up and was like, I have to go, so. But I do want to be respectful of everyone's time also.
I mean,
You did great.
mine didn't give me when I did that, it didn't give me a footprint for the RP2040, so just heads up.
Oh yeah, because I didn't send the footprint with it.
It's alright.
I'm sorry. Probably update,
that's what I'm doing
update,
right
and you'll
now.
get the footprint.
I'll go
Just
blue
get the new. Oh, I see you're already doing it. He's
Yeah.
installing it right now.
I'm doing the same thing. I'm updating to 7.0. Just
Alright.
Wait,
Thank you.
7.0?
7.0 is the new
Oh,
release.
7.0 came out. Awesome.
Yeah, I was like, I'll try that.
So I'm actually, sorry to cut you off. I guess one last thing. I'm actually going to finish this design myself and send it in individually ahead of everyone so I can see if there's a mistake with the way I'm telling everyone to use the RP2040. And when I finish that, I'm going to upload it to Discord so anybody can look at it and compare it to do their own. Between now and the next workshop. Like, I'm probably going to do that towards the end of next week, so that by the next workshop, I will have hopefully a physical board in hand to show everyone. If anybody has a design they want to do now, they could send in with that too. But
How many weeks are you planning on doing this?
how many? So 2 more workshops after this one. And my hope, next one's going to be the last workshop I'm talking about the software. The last one just to get together and get them working. So.
Yeah, and we'll place just one order, for,
Okay.
like one big order, I think on the 4th workshop.
Or I want to place them. I want to place the order like a few days after the 3rd
Yes.
workshop.
But
That way
just-
we have the boards at the 4th.
Yeah, just one big order, so we can use the IEEE money to order that, because shipping will cost a bit.
Yeah, it's only going to cost us like $5 a person for boards
Yeah,
plus the shipping.
yep. So, alright, thanks everyone.
Thank you.
Yeah, updating works. You just import all your old files.
Sweet. I'm actually not on version 7 yet. I've been waiting for it because version 7's adding a bunch of features I've been waiting for. I think we natively have support for teardrop pad connections in 7. It was one of the things that was on the roadmap.
I don't know what that means, but it sounds cool.
I don't know. Probably talk about that actually, because that's one of my pet peeves.
Are you still streaming?
Yes, I am still streaming. The Pico goes over here.
I just wanted the title to
Hey, that's you guys got sticky notes.
Sticky notes?
Yeah.
I have some.
Like for a circuit board or circuits? Yeah. Oh, yeah. That's a very good question. I don't know that website that has like pre-made ones. If you want to look from design, look up open source hardware. And there's actually like a little bit of a wall on stuff. And the idea of open source hardware is like sharing things like your circuit board designs.
Yeah, so this is a review for the physics.
Actually, there's a website.
It's gonna be.
During ECDs, I don't even know if it's still around.
You have to do this.
I forgot that existed, but now you kind of reminded
Just
me.
say like think of a design, nothing pops to my head. I'm like, I don't even know what I'd start with.
That's why I was like, I'm trying to show you guys, like, do some lights. Just literally do some lights and have some pins on there. And you can run code on it, and, like, it'll be cool, and you can see it, and then think about it. And you have to, like, so this was a design I did. And this is the motor driver. So I have Arduino, all the support stuff for the Arduino. I have these huge MOSFETs to drive the motor, and I drive the output the same pretty much exact way I just showed with the LEDs using these. These are the ones I have a reel of. To drive those, so it's like amplify then amplify to get to the motor. But this was, I was thinking, I want to drive a motor. How do I do that? And started reading about it. And this one looks like, I'm really not worried about the capacitor being detached, because this one's already fried.
Oh, well, there you go.
How did I get fried?
So actually, this is actually kind of an interesting story on this. This was in class I was taking called Engineering Analysis over at North Idaho College, and everybody wanted to do RC cars, and we only had like a budget of like $40 for each team. And if you look up like a motor driver, you're gonna pay like $40 for a single motor driver, and people wanted like several of them. So I was like, hey, I feel like trying to do a motor driver, and then I went and designed this circuit board, and this is the way it came from the manufacturer. So there were some components that they didn't put on that I had, so go and solder it all on. So I made like 60 of these, and then handed them out to all the students in the class and showed everybody how to solder them up. So.
At North Idaho?
Yeah, over at North Idaho College.
Two motor drivers.
Yeah.
Some other things they don't already have on.
Yeah, that would be helpful for your.
This circuit is, I can actually, since you asked that, I'll go post what I can in my projects. Not that everything's perfect in them, but if anybody wants to look through. This type of driver is called an H-bridge. So it is. Do you talk about anybody who's taken microelectronics too? Do you guys even talk about H-bridges?
Not to my memory.
This is kind of why I want to like make our general meetings of things, so we can go talk about things like, here's a circuit we haven't talked about that's useful. What is an H-bridge? What the heck's an H-bridge? You can go look up. There's a bunch of stuff on the internet about H-bridges. I designed this before I finished Circuits 1, and it worked perfectly fine. This board actually, no mistakes on this board. Oh, actually no, I back up. There was one mistake on this board. My one mistake on this board is this is actually an adjustable type regulator, and I picked resistor values that were too large for the adjust pin current. So it ended up being, instead of doing the 5 volt output I wanted, it did a 6 volt output, which turns out Arduinos do not fry when you give them 6 volts, so it worked perfectly fine. But that was the one mistake on this board, but it pretty much just worked.
Yeah, so it's just the resistor values you picked.
Yeah, so I did like
output.
I did like 50K and 100K or whatever, and then the current was like 200 microamps or whatever going into that pin, regardless of your resistor values, which ended up, it worked out to being a volt off. So then I found later the simplified formula I was using didn't work for that high resistor value. So I'll post this design and a couple others. I think I've already posted the Squid Game one, which was, it's kind of buried in here. With that design that I showed a few times, which is my recent thing. There weren't any mistakes on that one. That one worked out. And that was a stepper motor driver. So I guess motor driver is one of those things that's like analog that you can do. That is actually interesting to figure out.
Yeah, for our capstone project, we're going to have to use some motor drivers.
What's the project?
So we're doing like an automated tennis ball launcher kind of. So we're just going to buy a tennis ball launcher, put a camera on it, and have that detect a human, and then hopefully connect 2 motors that'll make the machine turn left and right, up and down.
Okay.
And then follow the person and shoot the ball.
So I would actually look into, I would use stepper motors.
That's what we were thinking.
Where are they? We actually have them in here. You guys could probably use. You can't keep them. They're the clubs, but.
I need to look up like how much torque they can handle, like all that, because I have no clue.
These ones we actually have the data sheets for. So you might have to gear it. I don't know for what you're doing, but we have a whole box of them for projects. And
You guys have the data sheet for them?
Yeah, we have the data. We just bought these like last quarter. Where's my thing? Well, maybe I am still missing one circuit board out of this. Or it's still in the box. There it is. There's nothing soldered on this, but this is a design I did before I ever started school, before I ever took this one. Yeah, the same one. And this is for a stepper motor driver. It is, like I was trying to make a point earlier, they try to make the chips as easy to use as they can. So this chip takes as an input an interface step and direction. So if step is high, go one way. If step is low, go the other way. And then, if direction is high, go one way. If direction is low, go the other way. And then every time it gets a pulse on the step pin, it goes and advances your stepper motor 1 step. Do you know how stepper motors work?
Kind of. I'm very limited. I was starting to look them up last week, but that was it.
So one of the best things to understand a stepper motor, spin that with your finger.
Yeah, you can feel all the pulses.
Yeah, so it's literally, there's a magnet in there, and every time you do a pulse, you can feel like click as you go through it. It's a discrete location in there. So every step it advances by one location. And you can look up, there's a lot of information. A lot of people use it for hobby things, so it makes it really easy to find information about stepper motors. But so every time you give it a step pulse, it will advance by a certain amount. And it happens to be by default on these with no microstep in it, I'll get into. It's 200 pulses per 1 full revolution. So if you go and set up your timer to output a pulse every certain time, and then you run it for 200 overflows, or like you have an ISR, and that ISR says that it's overflowed and reset 200 times, and then you stop it, then you'll have done a full rotation. So, and I actually like wrote a library for.
So you guys can use this for testing.
motors.
Yeah, you guys want.
We'll probably end up buying some too, just to make
Yeah.
sure. But be curious to know which one these are.
I think I just looked. Yeah, take a picture. Yeah.
We're only gonna need one up there, right?
Now we're gonna need two if we want to do our tilt too.
Oh, yeah.
All right.
But then yeah, might have to figure out gearing,
It might.
how much torque.
These give you a surprising amount of torque, too. Even with these, there are better drivers than this. This is the DRB 8825. It's like very integrated. It'll tell you exactly how to design the circuit for it, and then the way I have this board designed is. This is the connector. This comes with the stepper motor. There we go. So that plugs in. If you hold that for a second. And then literally
Plug into the board.
plug in there. Now I can run whatever code I want on this and
It'll send it
to drive that. And I actually wrote a library for this to give it commands. And this project was, this design was about 12 hours start to finish on it. And the code, including the code
Really?
on it.
That's
So
fast,
it's, but that's only because I've done
yeah.
the
That'd take
DR
me probably 5 days.
This one was a week, right? This was a week, and you go and if you look at this and compare it to this, I've done almost the exact same things here that I did on this board in this design. So you see, there's
It
like,
just depends when you were doing, how much knowledge you had.
yes, this was before I ever started school. This was this last summer.
Yeah, 12
So you
hours.
see, I have 2 capacitors here. Look, I have 2 capacitors here, and I've got. So there's a bunch of there's little analog things you have to do, but they're nothing you can't do after circuits 1 easily, as I did them before then. It breaks it down. They give you the formulas in the data sheet how to use it. They're like, oh, this needs to have
The
this.
data
this,
sheet's
this.
for the chips.
Yeah, the data sheet for the chip.
Okay.
They like break down how to do it. So, but yeah, so I just have 2 outputs on this.
Then how do you decide what chip you want to use?
So that is an art into itself, and the only way to get good at that is literally to go and sit down and try to find a chip to use. So if I already know a chip I want to use, that makes it easy, of course. But chances are I don't. What I go do is I go like into Mauser or DigiKey, and I just start doing the parametric search and looking around and trying to see what's out there. I try to do search terms, try to look through the chips.
And the chips that you look at kind of tell you what they're used for.
Yeah, so it's like, okay, so you want to do here.
Stepper motor, yeah.
I'll go and go to Mauser right now and show you. So we want to do a stepper motor, so we're going to go and look up stepper motor driver on Mauser. And you'll see, okay, well, this is going to probably be in this motor / motion / ignition controllers and drivers section. Maybe this didn't quite get what we want. So I'm actually going to go to this and be like, oh, there's inside of this, without the search term, we have stepper motor controller / drivers. So let's just do that. And then there's all these things like, okay, what voltage are you planning to use?
Which we don't even know yet.
You don't even know yet. Recommendations for stepper motors?
24 volts is a nice.
Yeah, 24 volts works. So this particular,
Really high.
the DRB 8825, which I found actually goes up to 42 volts, which is a weird number, but it's great for 36 with some headroom. The higher voltage you can deliver to, so in the stepper motors, when these go and move, it literally has a coil in there. So it has like a permanent magnet in there, but also a coil. And we could actually take this apart. Do you want to see the inside of one?
Yeah.
Let's take it apart.
I put it right here.
We take one Hawaiian.
And what was the other kind? Was the
Those are spinach feta cheese.
I just don't think you're
Yeah.
He's never teaching the class like this.
It's fine. We want to.
Matter.
I just realized the stream's still running, so people who look at the recording later can listen to this whole conversation. Maybe they'll find the stepper motors interesting and haven't clicked off the video yet. Or people who weren't here and are watching at home. I actually like that these have that cord as a separate thing. So have you taken 401?
I'm in 401.
You're in 401. I don't know, does he talk about things like EMI and
EMS, how
and like the fact that if you use something that's long, you're gonna fail emissions?
Yeah, he's touched on it a little bit. I think we're kind of getting to that now.
he does what we're doing right
We get the red sub.
Yeah.
Yeah, I had covers much as I wanted to today. I'm actually a little disappointed in myself. I didn't want to lose everybody, but I also wanted to get some stuff done. So it's hard to find the balance.
Yeah, it's kind of. And yeah, like you said, you were talking like the entire time anyways. So.
Yeah. Alright, so I just removed the 4 screws and popped the back off this.
Yeah, there's
So you can see there's all the coils in there, and then this right here is your permanent magnet core. So bearings, permanent magnet core, shaft, and then that around it. Mm-hmm.
Oh, that's EMAG, yes.
Yeah.
Lorentz force.
So yeah, go ahead and take a look at that. Oh, and you'll see actually, in order to get 200 steps, you go around, there aren't 200 poles on here.
Yeah, Jack.
These are
You
offset.
want to
So you see they're
the
like
step-
offset
it's the
50-50.
It's like in a stepper motor, similar to
100,
the
100.
research project that you did. Like your project was on motors as well. Yeah, so we all have to do like a research project in
Okay.
Dr. Rogers EMAG, and then like
Yeah, mine is it's about a generator they use permanent magnet to make like wave to turn wave power into electricity. So, I was saying like the
Oh, okay,
waves
yeah,
and
like
stuff.
tidal power.
title. Yeah.
That's
So I'm just
when I was reading about tidal power, it seemed like they were the ideal thing they wanted to do is like have the whole thing come up and then like trap it and then put it through a turbine was the best thing to do as opposed to like individual tidal like paddles. But I don't know if that's the case for sure.
I'll bring it. Out of line, see what happens.
you say break it.
It's pretty hard to actually break them. But the reason I was pointing that out, so you have coils in them, coils have inductance. So those coils need to change every single step. So when you want to start moving more quickly,
Yeah, he changed it.
you're fighting that inductance to get the current up to the level it needs to be to move it.
we have
So
to-
the higher voltage you have, the what is tau for an RL circuit again?
Like a whole folder of like researchers.
Really?
Say, yeah. But I mean, actually like sit down.
Is it just?
like,
I want to say it's
start
RL
taking
because as L increases, it'll increase. It's probably just RL for tau equals RL for. Anyways,
because we
somebody heard me on the video and that was wrong. I would look it up pretty easy. It's been so long since I had this one. But anyways, your RL constant on current is going to have like your exponential curve in there. The higher voltage you have, the more you're going to get that to shoot up. So at 5 volts, I'm pretty sure with the internal resistance on these, and this is actually in the data sheet, you literally just Google that. It's on the
Yeah, I took a
website.
picture of this. I had it.
When you go look it up, it'll tell you what the inductance is. It'll tell you what the DC resistance is for each coil, and it will tell you what the voltage for full current is. So that's like if you just sat with a DC. What these actually do is they do what's called current chopping. So if it's rated for, I think these are probably, I don't know for certain off the top of my head, I think these are about 1.5 amps. What the controller does, what that controller I was showing you on this does for you, is it goes and says, you set a current value on it. So these do like an amp before they overheat. So we set it to say we want 1 amp of current through the coil at full tilt here. So it's going to go and apply that 36 or 40 volts or whatever to it,
it is.
until the current increases to 1 amp, and then it turns it off. And then when it moves a slight bit below 1 amp, it turns it back on, and it creates this very like messy looking signal, like in voltage, but in current, it's keeping, you know, it goes up and then goes and stays pretty much there at what it's supposed to be by turning it on and off.
Okay.
And that's the way these like.
Yeah, because she wants more.
That's the way it can use a higher voltage with it than what you need. And it's almost like having, I don't know what circuits are presented in the later classes. I only have like literally 4 electroengineering classes.
Like it was
So
alright. I gave myself like.
I think it's actually a few more than that now, but I don't know what
Yeah.
is specifically discussed later on. But you guys talk about buck converters in
We
any
haven't
class.
yet. One person's actually doing a project. I think Nat's doing a project on that. His research project.
On buck converters?
We just
Yeah,
started
buck
doing
converters.
it.
Yeah. Well, we haven't actually talked about that yet.
Yeah, I'm pretty sure. I'm pretty sure I saw something about bucking, bucking, whatever.
Yeah, buck and
Yeah.
boost.
Can somebody get that for me?
Through that kind of, they should see that.
Yeah.
Thank you.
So yeah, I feel
That
like
goes.
I feel alright. You know. Besides the
Yes.
How many people were?
You can see these are made down to a cost that didn't even claim up the flux on it.
There's something you realize, try turning
I had 6 people.
before
Six
you put
people?
this thing.
Wow.
It's kind of hard when
Did you
try
say
to turn it. And once you put this thing, it gets smoother.
Like
You see down
I
here.
can't remember.
Let me see as soon as I get this on.
Six people.
You know, just
Gonna be just around.
banded my.
Let me see it.
Put that thing inside.
That's good.
See?
So they're
It's kind of
Well, okay, so the reason it's going to be really hard to turn right now
It was
is when this is on, it's holding the bearing and it's keeping it's keeping the rotor from contacting the stator. Does that make sense? So in this, when we try to turn this, you can actually feel it rocks back and forth. It's touching the walls. It's not supposed to touch the walls, so if we're trying to turn it right now, it's going to grab the walls and not do it. What's giving me a hard time here is getting this little spring in.
Right, you know, and this goes like clean.
So
they have,
let's
like, the
see.
sliding-
That's what people. That's what they want people to see them.
Yeah,
Like the dance.
we went on that tour to that dam,
We
like
just
downtown,
put it
remember?
Oh yeah.
It
because that
pops
dam
right
was-
back out, so maybe if
yeah,
I'm
they had
quick.
that one room that was just like a mess. And
Yeah.
Is it up? Oh.
So because it's magnetic, and that spring they chose is steel apparently.
When you
Okay.
get a place like a apartment, that's where you
Nope,
can.
that's right. Maybe we'll just go. There we go. Got it.
I think
Now-
they could.
Oh. Oh, there we go. Now,
We'll see.
now we're good. Now we're good.
Did they ask about like actually stuff?
Yeah.
No, I didn't.
Stepper
have
motors are
my
fun.
resume.
Oh.
Yeah, because we only
That's
did the one event.
actually that'd be probably a great circuit if you wanted to do the DRV 8825. I can even send you my. I'll go and actually you can look up on your phone. I'll show you where you can find the schematic right now, and you can look at what's done on it. You have to read the data sheet. It's I want to say somewhere around 40 pages. Read the whole thing. Just read the whole thing. You learn so much by doing that. If you haven't done that type of thing before. Yeah, that's like if you're doing circuit design as a job, that's your job is reading data sheets all day to do the design. Spend more time on the CAD software is cool, but it's like your tool to do the design, or like to show what the design is, but to actually do the design, you're reading data sheets. So Google GitHub IEEE Spokane Squid Game System, and we have a GitHub repository that's public.
Yeah, I've been applying like to lots of places.
IEEE Spokane.
Yeah.
IEEE EWU, sorry, might not say
Trying to
Spokane.
find 1 or 2 every month, so like at the end of all that 6 or 7, hopefully.
This one?
Yes, that's the one. So click repositories there. Squid Game System. And go ahead and click view code. And control PCB.
In DC or something.
And this right here is the KiCad files for that design.
I did see
And you're not gonna be able to view it because it's in GitHub, but you can download it to your computer. You can go in the repository. It's public.
Makes sense to me because it's a big city.
And actually, before you go one level, before you go one level deeper in here. So inside of Squid Game is
My
the.
aunt's family.
I would spend summer in
Which one did I do?
the winter.
Wrong.
A lot of
this right here is the
In terms of Vista,
library that I wrote
they
that
were from ASU.
controls the driver using. This is with Arduino though. It's not too bad.
Yeah.
Yeah.
like
But and
from-
then
using a
in
Raspberry
there's
Pi,
the
basically.
everything
no,
from
it's
University.
Arduino. So
It was-
it's using this is the ATmega 328P
Yeah.
that's on an Arduino. I'm not really using Arduino functions. I'm using the registers except for UART being so much easier to do.
Yeah.
It's always in June, and it's just always so hot.
Yeah, the same thing, so that the school got off,
Yeah.
like, pretty early.
We should definitely have more coding classes as electrical engineers. I feel like they're just gonna throw us in and we don't know anything. If we didn't do projects on our own.
Yeah. That and the other thing is when talking to people, our C programming for engineers class isn't that rigorous.
It was very basic.
So I've told you guys that pointers are covered just near the end.
Yeah.
I went out of my way to get out of that class. I worked it out, I'm taking CSCD 445 GPU computing instead of C for engineers. So it's like I'd rather take a senior computer science class instead of
No, I
really basic C programming that I did like before I ever started school. So I like, so I was a machinist for a lot of years and I started doing electronics as a hobby. And I was like into RCs and like motor controls and stuff. So that's why a lot of my projects are based around motors because I was like, how do I do this? How to design this and make this work? And then I was trying to do something more intense and like needed more RAM. And I started looking into microcontrollers that had DDR memory controllers. And then it was talking about, the data sheet talked about impedance matching and I didn't quite understand it and I couldn't quite get it at the time. And then I was like, what am I doing? I just really need to finally go to school for this stuff. Why am I waiting around? And I started school not that long after. And I abandoned that project because I got busy with everything else. But I was like, I need to go to school just to figure out how this works. It drove me nuts. I couldn't understand it on my own. So I like learned how to use and design circuits intuitively before ever being able to actually like solve them using calculus.
And I bet that helps a lot when you're going through the classes too, because you already have a good understanding of everything.
I try to not be too annoying, but I like, so I'm in microelectronics right now, and like 4 times so far in this course, like Dr. Who I really like Dr. Will's lecture, that he'll be like talking about a circuit that uses a transistor or a diode, and he'll say what it does. I'm like, no, it doesn't. It's like, prove it. I'm like, well, kids, he didn't even do the math. I could look at it and tell you. And I'm not that. What's sort of like, I'm not that aggressive about it, but like he showed like a rectifier circuit, and he showed like a jump, and then like a hump, and then down. It just starts smoothly at the hump and goes. There's no discontinuity there. And he was like, at first was like, check it out, and then he was like, he got a little sassy. He's like, do you want to go show everyone on the board? And I was like, okay. And then I went and tried to explain it. But it's because I can look at it and I can see it intuitively. Like a lot of hours of file stack, a lot of hours building the circuits. It does really help to understand it. I don't think there's a replacement for that educationally. Sorry, I'm gonna slide in here to put this back. To just spending a lot of time. I own 4 oscilloscopes. I have a massive dragon board of electronic components. And for like 3 years, in my spare time when I felt like it, when I wasn't chasing girls, I like, they were right, I'm sorry. I'd go and work on my projects, so I just enjoyed doing that, and I'd love to go and tweak it and see what it looked like in an oscilloscope and everything else and read about it. So
Yeah. I wish I would have had that passion before I started this.
Yeah, talking about
It's kind of just like a random degree. I was like, oh, this sounds cool. I'll
Yeah,
do
we have,
this.
so, I think.
And yeah, when you've done no projects or anything, and then they're like, here's your capstone, do it. And we're like, oh, we don't even know where to begin.
Another workshop in the spring, so.